So, welcome to this lecture about virtual memory management for NUMA architectures. And to give you a quick recap, last week we talked about virtual memory. And virtual memory in the context of operating system means that we want to have virtual addresses for our application and for our processes. And we do that every process lives in its own virtual address space. And one reason why we do that is that we want to have protection, that one process cannot influence the other process in a negative way. And these virtual address spaces, they are established by the memory management unit. And the memory management unit translates the virtual addresses that are generated from the CPU with the help of the page table tree to physical memory addresses. So the page table tree encodes this mapping from virtual addresses to physical addresses. By the page table tree we can have an arbitrary mapping between those two address spaces. Okay, so if you now come from your computer architecture course and you think, okay, perhaps all memory is created equal. So you might have the idea that you always have homogeneous access times, that you live under a unified memory access model. And for a long time this was very true. All memory accesses were equally slow, for about 100 nanoseconds. So your CPU might have looked like that you have a CPU package down there where 4 CPUs are very closely connected to each other, and to the CPU package externally is the memory attached to. However, if you want to have a lot of CPUs, hundreds of CPUs, it's not that easy to build this tiny integrated CPU block. What you have to do is you have to split up the CPU package into multiple packages, which we now call NUMA nodes, for non-unified memory access nodes. And those CPU packages, those nodes, have a locally attached memory. And if they access the physical memory that is locally attached to them, they have fast access times. However, if they want to access memory that is attached remotely, for example, you are on a green CPU and you want to access the blue memory, then you have to go over an interconnect to the other CPU package, to the other NUMA node, and then access the memory of that NUMA node. And this results in a situation where different accesses from different CPUs on the same address, like we see it here with our page 3, have different access latencies. If you come from CPU 0, it takes you 150 nanoseconds. If you come from CPU 1, it only takes you 100 nanoseconds. So we have now this difference between local and remote NUMA memory. And this poses a challenge for our operating system. So what we should do is we should minimize the off-node accesses, because those accesses are costly. They slow down our application. However, these applications have the problem that they expose different access patterns, unknown for us as an operating system, but those access patterns also change over time. So what we have to do is we have to do allocation and migration policies. So in the end, all this boils down to a scheduling problem. Where do we allocate physical memory and where do we place our threads? And in this lecture, we want to focus on the memory allocation part. So the simplest way how to deal with the situation is to have a partition system. We simply ignore the existence of the interconnect and say every process is pinned to one NUMA node, all the threads run on the CPU cores of that NUMA node, and we only allocate physical memory that we display in the virtual memory from that NUMA node. In this case, everything is green. Perfect NUMA latencies, only local NUMA latencies. That is great. However, now we have an artificial cap on the number of CPUs that we can use for a process, and in the NUMA node, those CPUs, and also a cap on the memory. So we cannot grow very, very large processes that could make use of the whole machine. So this is bad. Another way to do this is to have an interleaved allocation. We now get rid of this process thread pinning, and we say we simply used an interleaved pattern on the virtual memory surface where every other page on the virtual memory is allocated from a different NUMA node. So we balance out the memory consumption from the different NUMA node. And this is good, better as before, because we now have average NUMA latencies. if you have 2 NUMA nodes, you already have 50% chance of local NUMA access and 50% remote NUMA access. But still you have remote NUMA accesses with that long latency. And this gets worse if you have more NUMA nodes. So if you have 4 NUMA nodes, you're already at 25% chance of a local NUMA access and 75% chance of a remote NUMA access. So this is not really scaling for our application in general manner. The third policy that I want to show you is the first touch policy, which is the default variant in Linux. And the idea there is we make it dependent on application behavior from where we allocate memory. So we say the system, the application, requests memory, and on the first touch to that memory, from the first memory access, we look from which core, from which NUMA node came the access, and then we allocate memory from that NUMA node. For example, here, this green thread accessed this page 1, and since it's green, we also allocated a green page from NUMA node 1. And this is good because it brings us a good perfect latency if the access patterns are very static and we don't migrate threads to other cores. However, access patterns are not static and we want to migrate threads to other cores to do load balancing. And to solve that problem, we have also to do something about that. The idea is, couldn't the operating system migrate the data that is stored within a memory page to another NUMA node? So we only can migrate data, we can never migrate memory. It's soldered in. You cannot migrate a piece of hardware, not with physical access. So how do we migrate data to the thread that wants to access it? For that we have to do several decisions. We have to ask which pages do we migrate, when do we migrate, and to which NUMA node should we migrate. And the problem is the operating system has not the slightest idea about the DRM accesses that are happening. Because the operating system is not active. In the usual case, the operating system is a passive component in memory, and only if it's explicitly activated by interrupt or system call, it knows something. And we don't have hardware to trace all the memory accesses and would be too much overhead. So we have to come up with a better idea. The idea is to use the memory management unit to establish a complete access protection. We forbid all the accesses on our virtual memory interface. And then we wait for the next access, read or write, doesn't matter. And when some thread accesses that memory, triggers a page fault, triggers a trap, and the CPU does activate our operating system. Now we know, okay, the current running thread on this CPU wants to access that memory, and therefore we can look, was the access to this page that's below that would have then been a local memory access. In that case, we only remove the MMU protection. However, if the access does not match, so if a green thread accesses a blue page of physical memory, we migrate the data to a new page. In this case, we allocate a green memory page, we copy the data from the blue page onto the green page, and then we install the green page within the virtual memory. And from then on, all the accesses are local NUMA accesses. So what this does, it introduces a statistical process to move data to the accessing NUMA node. Why is this a statistical process? Actually, you would like to migrate data to the memory node, to the NUMA node that has the highest amount of accesses to a page. We only do it on the first touch after we establish protection. So this only gives us a chance that we got the right NUMA node. However, if you do this often enough, and if you re-establish this and do it often, that you re-establish the access protection, you get a statistical process that moves memory around. And if you think about it, what we have done here is that we have repeated the first touch policy. The first touch policy was that on allocation time, we decided from which NUMA node should we allocate memory. And now we provoke the situation where we can reconsider this decision. Yeah, and so this is integrated in Linux 3.8, and